Hi, everyone. I'm here today to present our survey on integrating foundation models, specifically large language models and vision language models, into reinforcement learning. We submitted this survey to ICHCAI 2025, and it was accepted. Okay, so we have a whole bunch of co-authors. I'm not going to mention everybody, but I will mention some people that are in the room. First, we have Masood in the back, and my co-supervisors, Osmar here in the front, and Matt, who is online today. So because we're going to be talking about how foundation models are integrated into reinforcement learning, I want to introduce a few preliminaries about each topic independently. So first of all, reinforcement learning is a framework for sequential decision-making. We have an agent interacting with an environment. The environment provides the agent with a state, and in response, the action selects an action based on that state. The environment then provides the agent with an updated state and a reward. The goal in reinforcement learning is to learn a policy that maximizes the expected discounted return or the expected discounted sum of rewards. So what are some of the main strengths of RL? First of all, RL only requires a scalar reward for the agent to learn complex behaviors. And the agent learns by interacting with the environment in a trial and error fashion. At the same time, algorithms often balance exploration with exploitation. Also, RL has the ability to transfer a learned policy to a new task, and the policy should work well on that task. Furthermore, RL enables adaptation to dynamic environments. So what are some of the main weaknesses of RL? And why would we want to incorporate models, foundation models? Well, first of all, RL is sample efficient. Also, the training can be very brittle. For example, small changes in the hyperparameter settings can result in large changes to policy performance. Also, on the previous slide, I said one of the strengths of RL is that the policy can be transferred to new tasks. But this isn't always the case, so generalization is inconsistent. Also, long horizon tasks present a challenge for RL, where the agent interacts with the environment over long sequences and only receives a reward at the very end. This makes it hard for the agent to assign credit to any particular action for achieving the goal. Finally, RL relies so much on the reward, and reward design is actually a difficult problem. So first of all, there are tasks where reward is difficult to specify. For example, a kneeling task, asking a robot to kneel on the floor. Also, when you're designing rewards, you have to test them. And sometimes they may lead to unintended or unexpected behavior, not what you originally intended when creating it. So what are foundation models? Well, foundation models are large pre-trained models. Today, I'm going to be I'll be interchangeably using foundation models with large language models and vision language models. But foundation models is a very broad category and includes more types of models. But today we're only looking at large language models and vision language models. So how are these models trained? Well, first of all, they're trained on lots of data, including books, images and their annotations, as well as internet data, including Reddit, Wikipedia, and YouTube videos, along with their time-aligned transcripts. What does all of this data have in common? Well, this data comes from humans. So essentially, these foundation models are being trained on human data. And more recently, they're also being trained on simulated human data. So a question came to our minds, and it was, can we integrate large language models and vision language models into RL And why would we want to do that? Well, humans communicate in natural language, so it's easy for us to specify a goal and pass that to the foundation model. These foundation models that are trained on all of this human data and simulated human data can serve as rich priors. Also, some of the emergent capabilities that have arisen are strong generalization. So these foundation models can perform well on a variety of tasks. Also, chain of thought reasoning was at one point an emergent capability, meaning that the model wasn't explicitly trained to think in a chain of thought, but it could do that. But I believe that more recent training does include this. Also, another emergent property is in-context learning. So this is adding information to the context of the prompt such that we can elicit better outputs from the model. Also, these foundation models have the ability to self-critique and self-refine their own outputs. Okay, so now we're going to start talking about our survey. So first of all, we submitted this to ICHCAI. So we had a very limited amount of space. So we had to have a very strict inclusion criteria. So we limited ourselves to peer-reviewed papers. The LLM or VLM used in the paper had to have a transformer-based architecture, and it had to be released on or after GPT-3. They had to have at least one task that was modeled as a Markov decision process. And they had to use the reward signal in some way to improve the policy. Okay, so one of our contributions to this paper is a taxonomy. And to the survey. And we essentially split all the papers based on how the foundation model was integrated into the RL framework. In the first one, the foundation model itself was used as an agent. In the second one, as a planner, and in the third, reward. Each of these categories is further subdivided into, for example, agent into parametric and non-parametric, planner into comprehensive planning and incremental planning, reward into reward model and reward function. And we're going to dive into these on the upcoming slides. To start, here we have a table that we included in our survey that outlines all the papers. On the leftmost side is our taxonomy. The main objective of creating this table was so that others could see patterns among the data. Okay, so now we're going to start talking about each of these sections one by one, starting with foundation model as agent. Okay, so it's not formatted on here, right? I don't know if it transferred to Windows differently, but anyway, the first category is foundation model as agent. Here we have the foundation model itself interacting directly with the environment. And a result of this interaction is that it creates trajectories. So a sequence of state, action, reward, next state pairs. And these trajectories or subtrajectories are saved either to be put in a storage to be later used in context, or they're used to help fine-tune the foundation model. So the very first one we're going to look at is the subcategory of parametric. Here, the parametric means that the foundation model's weights are adapted. And here, basically, the trajectories that are generated through interaction are used to fine-tune the foundation model. Often, these methods use parameter-efficient fine-tuning techniques such as LoRa, adapter, and prefix tuning. There are one or two papers that were included in our survey that actually fine-tune the whole model. Our second category is foundation model as agent non-parametric. Non-parametric indicates that we do not modify the authors did not modify the weights of the foundation model. Yeah, so the foundation model is frozen, and the trajectories that are generated through interaction are saved to a database. When it comes time for the agent to make an action decision, It can retrieve relevant examples from this database to serve as an ideal way to behave that gets added to the context, and then ideally the foundation model should output a better action. So what are some of the benefits of these methods? Well, parametric methods are great if you're using the parameter efficient fine-tuning techniques because you still have the broad capabilities of the original foundation model, but you can also improve task-specific performance. Non-parametric methods are great because you don't have to fine-tune the models, and you can improve performance through in-context learning. Non-parametric methods are also better, especially when the weights are proprietary and you don't have access to be able to fine-tune them. So the first thing I'm going to do is start by presenting one paper in this area. And the name of this method is Expel. This paper was presented at AAAI 2024, and it comes out of Beijing, China. So what are the author's motivations? Well, LLMs excel at broad reasoning, but they struggle to retain task-specific experience. We can fine-tune the model, but doing so is compute heavy, and often the parameters are closed source. So also one additional problem is that fine-tuning can degrade generalization, particularly when you're fine-tuning the entire model. So the research question of the authors was, can an LLM agent autonomously learn from its own experience, boosting performance across tasks with no fine-tuning? Okay, so Expel, their method, focuses on inter-task learning. And there's three main phases, which we'll go through one by one. First, experience gathering. Second, insight extraction. And third, inference. Okay, so experience gathering. I want you to focus on this subsection here first. What happens is a task is the foundation model is given a task, and then it interacts with the environment for that particular task for a single episode. If the interaction results in success at the end of the episode, that is great. If it doesn't, it actually ends up sending the trajectory and the reward that was generated to another large language model to self-reflect on what could have been done better. Then those self-reflections are added to the context or the prompt for the next episode, in the hope that adding those self-reflections will help the foundation model select better actions throughout. This is actually another method called reflection. And it's focused on intra-task learning. Now, Expel extends that work in two ways. Because Expel is focused on inter-task learning, so learning information across tasks, it introduces a task space with all tasks being different but similar at the same time. And it also introduces this new step where after the agent is given a task and tries an episode, it will generate this trajectory that is either successful or failed. It will save that trajectory into this database along with the result, success or failure, and along with the task. And if the trajectory is failed, it'll also save the self-reflection. So Expel will repeat this process, this entire learning process, for numerous tasks, saving all of the information into the same database.
One question.
Yeah.
You talked about success or failure binary. You get a score in general for how good it was, or you know it's yes or no.
I think it's binary in this case. Oh yeah, sorry. So thank you. It's Russ was asking, is success or failure binary in this case? And I believe that with the two MDP-like environments that they used, which is WebShop and ElfWorld, I believe it is binary. Okay, so then the next phase is insight extraction. So they've already collected all of this experiences and put them into an experience pool. And what they want to do is they want to generate a high level list of insights. So they start with an empty list. And first they look at success and failure pairs for the same task. So by looking at these success and failure pairs, they can identify what went wrong in that task. And if the LLM decides, well, okay, I've extracted what went wrong. Now, do I want to add it to the list of insights? And so these are the actions that the LLM has available to it. It can add to the list, which it does in this example. Okay. So every insight that is added to the list is given a default score of 2. The upvote action increases the score by 1, making it more important. The downvote action decreases it by 1. Edit has no change, I believe, but I have to verify that. So essentially, what you end up with is after doing 1 insight, you get a list of 1. The next thing that they look at is a list of L successes. So now they're looking at different successes across different tasks. These are trajectories of successes. And the general idea here is to extract high-level best practices on how to do these tasks. So this process repeats numerous times for all of the experiences in the experience pool. And the end result is that you should have a list of insights that help the foundation model do better on a variety of tasks. Okay, so looking at this image here on the right, we've covered A, where they gather experience, and we covered B, where they extract insights. Now we're looking at the purple section, which is inference. So the large language model or foundation model is given a whole bunch of tasks to be evaluated on. And the insights that were extracted are passed to the foundation model as context. Additionally, from the experience pool, it can capture, or it can retrieve similar tasks, successful trajectories for similar tasks to serve as exemplars to be added to the context for any task in here. So now we have 2 things that are added to the context. We have exemplars of good behavior for similar tasks and insights. Okay, so that.
So just to clarify, so then when this runs again, the exemplars get added to the context.
Yeah, so let's say you're doing task 1, it's gonna pull exemplars that are similar to task 1.
But like a multi-phase process now, so at the start, it looks at the problem and then decides it had some good about that time.
Right, at inference. And so then when you switch to a new task, it would dynamically retrieve new exemplars.
All right.
Robots, icons, and so on, and then
Sorry?
the robot icon, solve an island.
Yeah,
Where do we use it? And then why can't we do this using the language?
Well, I assume what is trying to evaluate versus what is trying to look at.
I'm asked with one is the robot icon, another is the opening.
I don't know why they did that. I'm not a co-author. I can't answer that, but I get what you're saying, yeah. The question is why do they have a robot here to represent the LLM as the agent? When they could use a symbol like the ChatGPT symbol.
For evaluation, is it held out tasks or is it just the six task things?
I believe it's held out, but I would have to double check that, yeah. Typically it's held out, but I have to double check, sorry. Okay, so I'm not going to cover these results in detail, but I want to give you a general idea. First of all, their method is in purple. It's the expel method. They compare it to imitation learning, a supervised learning method, and several different large language model agent methods. ACT, REACT, And then up here, R1, R2, R3 is reflection. They also do their ablations in here, showing how Excel works without any exemplars, so insights only, and how Excel works with no insights, but only exemplars. And the general idea here is that Excel has a higher success rate than all other methods.
I guess two questions.
Yeah.
First question is for things like imitation learning, as in training from scratch, you think data that was used for filtering, and then you just avoid the train, or is it a backbone foundation model pre-train and then fine tune not?
I can't remember that. I'm sorry. Yeah, it's been a while since I read this. Yeah. But I can follow up with you
Yeah.
and give you an answer to that. Okay, so the next section is using the foundation model as a planner. So in reinforcement learning, we call planning something totally different than the way this is used. So in planning, in reinforcement learning, we have a model of the environment, or we have an estimated model, but we use it to generate simulated trajectories. Here, planning is taking a complex task and decomposing it into a series of subtasks. So in this example, we have somebody requesting the LLM, can you get me a can of soda, please? And the LLM responds by providing a plan to locate, navigate, grasp the can, and then navigate back to the person and place the soda. Okay, so you can't see because of my formatting has changed on this machine, but I'm sorry. But this is comprehensive planning. So what this means is that the LLM is queried to create a plan, and it creates the entire plan from start to finish in one query. So the plan is in natural language. So we have to have this interpreter that converts it to a sequence of goals, because in these methods, the policy for some reason is often goal conditioned. So then the agent tries to execute that. And in some papers, if there's any type of execution failure, they will send feedback back to the LLM, and the LLM or VLM will replan starting from the point of failure. Our second method for planner is incremental. So here, the foundation model is queried with a task, and it provides only a single step of the plan at any given time, but it gives the agent multiple options to choose which step it wants. And then the agent will execute the selected plan. Here, the policy is often language conditioned, so there's no need for that translator module. So the agent executes the language conditioned policy, or it could be also learning that policy. But then if there's any type of failure, that can get sent back to the LLM along with the trajectory and the reward to regenerate a new single step of the plan. So what is the benefit of using a planner, like a foundation model as a planner? The biggest benefit is that the foundation model can take a complex task and decompose it into a series of steps that are much more easy for an RL agent to execute or learn. Okay, so our third category is using a foundation model for reward. So here, the foundation model serves as an indirect or direct source of reward that is given to the agent. Our first method is reward function. So here, the foundation model outputs a reward function in code. After being provided, so I'll just take a step back. So actually, the foundation model is provided with an abstraction of the environment. Often that doesn't include the reward. And then as a result of that, it generates a reward function in code. This often gets added to the environment code and then executed by the environment gets executed by the agent, and the agent learns a policy with that code. Now, some methods will incorporate a type of feedback. So they'll record various policy metrics. And then they'll add that to the context so that the LLM can redesign a new reward function. And we'll see an example of this in the paper that's coming up. The second option is using a foundation model as a model of the reward. So there's two different types here. First, there's reward model learning. So here the foundation model serves an indirect source of helping to get reward. The foundation model sees different trajectories and it is able to rank them. And then those rankings are passed into a neural net to learn a reward model. And then the reward model is actually the source of the reward for the agent. Now, the reward model right here and the agent's policy can be learned at the same time. The second option is using the foundation model directly as a reward source. So here, the foundation model will output a reward in textual format, and often they will have a parser to convert it to a scalar. So what are the benefits of using a foundation model for reward? Well, reward engineering requires a lot of human effort. It's like generate, test over and over. Also, in reward model learning with human preferences, that requires a lot of human effort in ranking preferences. So essentially, adding a foundation model to the loop can reduce human effort. And one of the things that I like most about this is that actually some of these methods can learn reward functions that either match or surpass those designed by humans. And we'll see an example of that in this paper.
Hey, Sheila.
Yeah.
Oh, yeah, no, I'm online. Yeah, I had a quick question. Could you go back 2 slides? Yeah, so here, you have reward model, and then you say like the LLM generates the reward directly. But then how is this different from the previous slide where you said that the LLM generates like the reward function?
Right, so this first slide here that I'm showing now, the LLM is not generating like a textual value for reward, it's actually generating the reward code. Python code that can be added to the environment code for that particular task. Whereas here, the foundation model is actually being given an observation and an action, and then it outputs a scalar in textual form. Does that make
Okay,
sense?
I see. Yeah, it makes sense. Thank you.
Okay. Okay, so let's look at this ICLR 2024 paper. Their method's name is Eureka, and it's coming out of NVIDIA, UPenn, Caltech, and UT Austin. So the author's motivations are LLMs are really, really good at these high-level planning, as we saw, but they struggle with low-level skills. But RL can master these low-level skills, but they require these carefully crafted reward functions. And as I mentioned previously, like finding a reward function is a trial and error search process, and it can lead to suboptimal reward. So the main research question in this paper was, can a coding LLM autonomously find good reward functions? And they framed their problem as a reward design problem. So here we have a world model with set of states, set of actions, and transition dynamics. R is a space of all possible reward functions. A of M is a learning algorithm that maps any reward to a policy. And F is a task metric, in this case, fitness, that evaluates a policy. So F is a human-designed metric. It's task-specific, and it's also a black box to the LLM or VLM. So the objective here is to find a reward R in the space of all rewards so that the learned policy maximizes the fitness. So I mentioned just a few points ago that the fitness function is actually human design. So what does this actually look like? So the authors are doing everything in Isaac Gym, and 2 of the environments that they use are Cartpole and Ant Runner. In cart pole, the objective is to keep the pole upright by moving each side of a box along a horizontal line. The pole can fall over if you move it wrong. So here, the fitness function defining how good a policy is how long the pole stands upright or up. And then in ant runner, one of the goals is to have the ant run forward as fast as possible. So here, the fitness function looks at, well, how far did the ant traverse? How far was the ant at time step t compared to how far the ant was at time step t minus 1? So what distance did it cover in a single time step? Okay, and this is an overview of their method, Eureka. It's an evolutionary search method. So starting here on the left, they provide starting here, they have a coding LLM, and specifically GPT-4. But here on the left, they provide the coding LLM with some context. So first they give it an abstraction of the environment. So they don't want to reveal the reward function for the environment. They don't want to reveal anything about the physics of the environment. So they scrape all the original environment code, only leaving information about the state and action components. And then they give this task description. In this case, it's make the shadow hand spin the pen to a target orientation. So with that information, the coding LLM is queried independent, like 16 independent times, generating 16 reward functions. Then they learn a policy with each of those reward functions within Isaac Gym. While they're learning the policy, they keep track of different metrics. So some of the metrics that they keep track of is the value of the different reward function components. So if we look at this reward function here, we see two components, average norm and average penalty. Well, average norm is actually not an important component, but average penalty is. So you can see here, they've kept track at various points, the value of that average penalty. They also keep track of additional information for each policy that's being trained. They keep track of the success rate, the length of an episode, the fitness value. So there's a lot of data that they save. After all of this training, they select the best performing reward function or the policy with the best reward function. And they pass it back to the LLM with all of the information about that particular reward function. And their hope is that they can take this information along with the reward function and use it to influence the next generation of 16 candidate reward functions. This process actually repeats 16 times, sorry, not 15 times, 5 times. I'm confused. Oh yeah, 5 times. And at the end, they have the best reward function for this iteration. Now they do have 5 different runs that are independent. So they end up in the end with 5 reward functions, but then they ultimately present the results for the best performing reward function across those 5 runs. So now we're going to see the results. I'm not going to go into too much detail about the results again. The key idea is that, let's take a look here. At this plot, blue represents Eureka. Their baselines are L2R. This is another like foundation model reward design system. Human is in purple, or this dashed line here. And then this orange or yellow represents a sparse reward situation. So the general trend that we can see here is that on the left, first, that the Eureka surpasses success rate of human reward. On the right, we see a general trend that all of the blue bars are at the level or higher than the human designed reward. And even for these complex tasks like ant and humanoid, it's quite high, and it far surpasses the human design reward function, and L2R, the other method that uses foundation models, does not even find something that works.
Question.
Yeah.
So we understand the idea of trying to find this, after every single action gets a response, but the overall goal is always good. The overall goal of keeping the goal upright and trying to get to this location. But the question now is, what individual, one step reward function operates? Is that correct summary what's going on?
Yes, so they're trying to find a. Oh, okay. Sorry, I have to repeat questions. Yeah, so you're asking. What is happening here? Like, is the reward going to be given after every action? Yeah,
But how do I translate that step to one action, generating reward that one? Another action, reward, so one of the pieces of reward that sides that the overall reward is achieved. Is that for somebody or?
that's the right summary. So basically, we're designing a reward function that is dense so that after every action, the agent receives a reward. Yeah. That's your answer to your question?
Well, it's writing the program. And then the program runs and you look at the duration of how long the whole stays up. And so then if it's successful at making the whole stay up for a long time, then the program does it.
That's right. So actually, we're designing in each environment, there's in the back end that runs that environment and defines, it computes the reward. So we're designing the code that computes that reward, but it is a dense reward.
All functions begin.
Okay, sure. Okay, and another key insight about their process, because there's 5 iterations, they wanted to see, like, is there actually improvement with all of these iterations of generate, select, mutate, and so forth, like, and they show that every iteration, their reward function improves. That's the general idea of these results.
Question.
Yeah.
That's the reward function. So in the previous part, the y-axis is success rate, right? But this
On this
is function on the policy learning algorithm as well, right?
Pardon me?
As conditions on the policy learning algorithm. as
Right,
well,
yeah.
Okay, so essentially recovering reward functions that are describing the task, but also provide good automatic programs for the policy.
Right, we're evaluating every reward function by the policy that is learned using that reward function under an algorithm A, in this case, that's PPO.
And I was curious if they have results about like how different the final reward function is as to what humans would have designed.
I don't know if they have that in there. Yeah, I'll have to double check it. Okay, so future directions. What is missing in this area? Well, one of the things that, that is really applicable mostly to LLMs is the representation problem. So a lot of reinforcement learning environments, everything from the observation, the action, the reward, everything is numeric. And when we're using foundation models, particularly large language models, we have to convert that to tokens and then back to these vector representations to be able to have these two things react or interact. So where do we stand on this? Well, currently, a lot of methods actually use very simplistic text-based environments. Like, I'm not sure if you're familiar with ElfWorld or WebShop, but those are some of them. Alternatively, some methods will have external translator modules that are hand designed by the authors of the paper. So we see an example of that on the right. Given this observation vector, the translator outputs some text and passes that to the foundation model. And then the foundation model passes an action in text back to the translator. And then the translator outputs a vector action for the agent to execute. Also, I've seen some methods that they actually make architectural changes to the foundation model, replacing the embedding and output layers with MLP layers and then fine-tuning those layers. So what are the gaps here? Well, using these external modules adds a lot of latency. Also, converting from numerical representations to text is information loss. There's a significant amount of information loss. So I guess one area that might be able to help is integrating VLMs Maybe we could use them to capture a visual image of what is happening and replace that with the vector observation. But again, this doesn't solve the problem about the action being vectorized. Our second one is grounding. So this mostly applies to the planning situation where we ask an LLM to generate a plan and it outputs a sequence of steps. Well, some of those steps in practice may not be achievable by the robot or the agent. And on the right, here's a perfect example. This robot actually can't bend very far, but is told pick up the apple, and it can't achieve that. So where do we stand with that? Well, once again, there are mostly external modules that will measure the feasibility of a single step of the plan. Some people also use very task-specific output formats, like prompting the LLM to output a very, very specific format, such as an array of ones and zeros that represent foot contact patterns for a robot. So these two solutions actually limit generalization massively because they're both very task-specific. And the second one, prompting the LLM to output very specific formats, can definitely inject bias and misdirect learning. Finally, our last future direction is action advice. So one of the problems with reinforcement learning is that it learns very slowly. So it requires many samples to learn. Where do we stand on this? Well, no work actually has been done in this particular area from the papers that we surveyed. However, prior work in RL has looked at whether expert teachers, whether they are expert RL agents or human teachers, can provide advice to a student RL agent such that it accelerates their learning. And the answer to that is yes. So one of the questions that came to my mind when reading all of these papers was, can these foundation models serve as a teacher, providing low-level action advice to the RL agent that is learning, particularly in the early stages of learning? So what are the key takeaways for today's talk? First, we presented a three-part taxonomy. Then we discussed each part of the taxonomy one by one, starting with agent, looking at parametric methods that modified the foundation model's parameters, and non-parametric methods that kept the parameters frozen, but used examples from a database to help in context learning. Then we looked at foundation model as a planner. We looked at comprehensive planning, where the foundation model generates a full plan in one step. And we looked at incremental planning, where the foundation model generates multiple options for a single step of the plan. And finally, we looked at foundation model as reward, focusing on reward function and reward model. In reward function, the foundation model outputs a Python code reward, which gets added to the environment code so that the agent can learn a new task. We also have reward model, where the foundation model will rank trajectories, and those trajectories will help in the learning of a reward model. And that reward model will pass a numerical reward to the agent. Also, the final one is we have the foundation model directly providing reward from text format, and then that gets parsed into a scalar format. And that concludes today's talk. So if you have any questions, I'm happy to hear them.